All right, we can start our review of mechanics of materials, and basically is a kind of chain of classes that come one after another one. We start with statics, then we go to mechanics of materials, and then we go to failure of materials. These three classes are tightly related to each other. So let's start with let's start by seeing what we see in statics typically. So in statics, we analyze bodies that are rigid. So which means that we do not consider deformations that occur on a certain body. Basically, there are three main components that we look at in statics. We look at the loads. Then we look at what kind of geometry we have for our structure. And then we look at what kind of constraints we have in our structure. So loads, we can have forces and moments. Geometry, we typically look at the sides of our structure, like the length of the beam, or typically. And then for constraints, we may have different type of constraints depending of what kind of structure we have. We can have fixed constraints, we can have pins, rollers, and so on. So basically, by combining these three pieces of information, from statics, basically we can determine the reactions that we have in our structure. Right. So when we move from statics to mechanics of materials, we still need all these pieces of information, because we still need to look at the loads that we have, the geometry, the constraints. We still need to determine the reactions, and then we move forward, because what we do, we basically remove the hypothesis of rigid bodies, and we start to talk about deformable bodies. So in mechanics of materials, what we do, we introduce new concepts that basically allow us to determine how a body can deform, so can change basically its shape and size after we apply a certain load, we have a certain geometry with certain constraints. So basically the concepts that we introduce in mechanics of materials are the concept of internal forces. So internal forces are axial load, shear force, bending moment, and torsional moment. Then we look at the concept of stress. And then we'll also look at the material properties. So we look at, for example, the Young's modulus, we look at the yielding stress, and so on. So basically, by combining all the information that we have from statics plus these other pieces of information, again, internal forces, stress, and material properties, then we can determine, we can determine if a material fails. And in order to determine if a material fails or not, we also introduce the concept of factor of safety. Basically, the factor of safety, and later we will go even more in detail on this, but the factor of safety basically tells us how far we are from having failure for our material. Is this familiar, this chain? All right, so now we can go more in detail to see all the concepts that we cover in mechanics of materials. And the very first thing that the very first concept that we cover in mechanics of materials is the concept of stress. So how many types of stress? Actually, even before that one, we should start by thinking of the definition of stress. How do we define stress? Force per area. So in order to determine the stress, we have to look at the amount of force that we have on a certain area. We divide that force by the area, and then we obtain the stress. So it's the same concept of pressure, because pressure is also some force applied on a certain surface. So the units are even the same. So in mechanics of materials, we have two types of stress. Do you remember? One is normal. What about the other one? And shear stress. Perfect. So these are the two types of stresses that we find that we can find in a certain beam, in a certain structure. So the difference between these two types of stress is the way how they are oriented with respect to the cross section that we are looking at. So the normal stress is perpendicular to the cross section that we are analyzing. The shear stress is parallel to the cross section that we are analyzing. So if we want to do a schematic of this, we have that if this is the cross section of our beam where we made our cut, we have that again the normal stress is perpendicular to the cross section. On the other hand, the shear stress is tangential to the cross section. Right. So typically, just to have a little bit of convention, we indicate the normal stress with the Greek letter sigma. And we indicate the shear stress with the other Greek letter tau. I think this, is very useful so that we all understand when we talk about sigma and tau. So sigma is typically the normal stress. Tau is typically the shear stress. There are textbooks where you can find a different convention. This is what I will use during the entire semester. Okay. Also regarding units, we said that stress is a ratio between a certain force and a certain area. So if you want to determine the average normal stress on a certain cross section, we go with sigma equal to P divided by A. So P would be the intensity of the load. You can indicate this with P. And A is the area of this cross section. We can also calculate the average shear stress that acts on a certain cross section. And we can use an analogous formula where we have tau average, again, average shear stress equal to a ratio between V and A, where V would be this component of the force, like the shear force. both of them are stresses, so physically they are analogous quantities, so the units are the same for both of them, and we use pascals, which is newtons over meter squared. So Newton is force, meter squared is area. So force over area gives stress. We can do a little trick. If you want to use different units, we can go with megapascal. The stresses that we obtain in a certain structure are actually in the order of megapascal. So if we want to obtain megapascal, we can use newtons and millimeter squared. Any questions so far? All right, and stress is, again, the very first concept that we find in mechanics of materials. Which one is the next concept that we find in mechanics of materials? After stress, we talk about strain. So how many types of strain can we find in a certain structure? Two types of strain, exactly like the stress, and exactly like the stress, we also have normal strain and shear strain. So in general, the concept of strain is related to the concept of deformation. So the general definition of strain is that strain is the deformation that occurs on a certain element due to an external load. And the difference between normal strain and shear strain can be found in the fact in how this deformation occurs. So when we talk about normal strain, it is basically an elongation or reduction of a certain element of volume. When we look on shear strain, it's basically the change that occurs in an angle within a certain element. So if we want to do a schematic of this, so for the normal strain, so if this is the initial, so if this is the element before we apply the load, if we have a normal strain, it means that we change the dimensions of this element of volume. So this one in blue would be the initial configuration, and this one in black would be the final configuration. So we have a positive strain in this horizontal direction because the length of the element of volume increases. So we have a positive strain when we have an elongation, and we have a negative strain in the vertical direction because the size of the element decreases. So positive strain, negative strain. When we look at the shear strain, we said that it is related to a change in angle. So if we want to do a schematic of it, so even in this case, this is the initial configuration of the element. Shear strain means that it looks like this. So here, if we want to calculate the normal strain, first of all, we look at which symbol do we use. We use epsilon. And we have that epsilon is equal to delta L over L. So delta L would be the difference between the final length and the initial length. And then on the denominator, we also use the initial length. So basically, by looking at this equation here, we understand if our element of volume becomes longer or shorter. If it becomes longer, it means, again, we have a positive strain. If it becomes shorter, we have a negative strain. Regarding the shear strain, we use the symbol gamma. Use the Greek letter gamma. And the equation so the strain, again, is the difference in the angle before and after and before the deformation. So it will be the final theta, which is the angle between the two sides of the element, and the initial theta, which is the angle between the two sides of the element before we have the deformation. Questions? All right, now that we know about the stress and strain, another very important concept that we cover in mechanics of materials, even if in mechanics of materials we kind of barely touch, but in failure of materials is basically critical, because most of our class will be about this concept. So we can start to review it now, and this is the concept of factor of safety. So as we mentioned before, the factor of safety basically tells us how far we are from failure for that specific structure, depending on what kind of material we have for our beam structure and what kind of loads we have and the intensity of these loads as well. So if you look at the formal definition, the formal equation of the factor of safety, this is how we write. So we have that Fs so the factor of safety is a non-dimensional number because it's a ratio between two stresses, and in particular is the ratio between sigma failure and sigma applied. So this sigma failure is something that depends on what type of material we have, and this is something that comes from the mechanical properties of the material that we have. This sigma applied depends on the loads that we have on that specific structure. So this one, sigma failure, again, depends on the material properties. So depending on what type of material we have, if it is a brittle material or ductile material, we define sigma failure slightly differently, because if it is a ductile material, we need to use sigma yielding. If it is a brittle material, we use ultimate strength. And then sigma applied is something that we need to determine by looking at what kind of loads we have on our structure. And this is like a very simple example, a very basic way of indicating this factor of safety. And we can go straight with this equation when we have a simple load, for example, an axial load only on our structure. But we know that in reality, in pretty much every field, our structures are subjected to combined loads. So we can have at the same time different types of loads, which means that we have to be able basically to work on this sigma applied through several steps, which includes more circle and combined loads first, then more circle, and so on. But the concept, like the physical concept of the factor of safety, is always the same. So again, it tells us how far we are from having failure for that specific material and that specific structure. So one question that we can have at this point is that this ratio, so this number basically increases if we reduce the applied load, or if we increase the sigma failure, depending on what type of material we have. So if we want to reduce this, which is basically something that we can do by changing the geometric characteristics of our structure, we can think of, okay, how about we always have like a very small sigma applied? We make our structures very, very big, so we have small stress, small applied stress, so we always have very big factor of safety. Why we can't do this all the time? So as engineers, what kind of consideration do we have to do? What? Cost is one consideration. What else? Space. What else? Weight is another one. Anything else? So these three are very, very important aspects that we have to consider, because, for example, if you think about an aircraft, weight is like an very important parameter. So we as engineers need to make sure that we have a certain factor of safety, but we cannot make our structures as big as we want, because when we increase the factor of safety, it means that we increase the size pretty much of our structure. We increase the size, we increase the weight, and then the aircraft will not take off anymore. Make sense? So in different fields, there are values of, typical values of factor of safety. So for example, for an aeronautical structure, the factor of safety can be in the order of 1.5, 1.6, where the weight is like very, very important. If we look at a building or a bridge, the factor of safety can be higher, like 2, 3, and something like that. Of course, if we have a smaller factor of safety, on the other hand, we have to go through a lot more tests for that specific structure in order to make sure that our structure can withstand the loads that we are planning to apply on that structure. Make sense? Questions? And again, during this semester, we'll go through this concept in depth. Any question? So now I would like to go over the different type of loads that we can have on a certain beam. All right, on a certain beam, on a certain structure, we can have, let's say, two families of loads. So we can have forces and moments. And for each of them, forces and moments, we can have two types. So the two forces that we can have on a certain beam are axial forces and transverse forces. Also for moments, we can have two types of moments applied on a certain beam. What are they? Bending moment and what? And torsional moment. So we have these four types of load, and each of them is responsible of a certain type of stress on our beam, right? So here, I would like to emphasize on how we distinguish a load from be axial or transverse. In order to understand if a force is an axial force or a transverse load, we have to look at the orientation relative to the axis of the beam. So beams are slender objects like this, which means that we should be able to identify one dimension which is much greater than the other two. So in order to understand if a force is an axial force or a transverse load, we have to look at the relative orientation with respect to the axis of the beam. If the force is aligned with the axis of the beam, it is an axial force. If the force is perpendicular with respect to the axis of the beam, it is a transverse force. So the absolute orientation of the beam doesn't matter. So, for example, if we have a beam that looks like this, you know, this would be an axial load. If we have a beam that looks like this would be an axial load as well. If we have a beam that looks like this will be the axial load as well. So in each case, the load, the force is aligned with the axis of the beam. So in all these cases, these forces are axial forces. On the other hand, for this beam here that is horizontal, a vertical load would be a transverse force. Here, if the if the beam is vertically oriented, the horizontal force will be a transverse force. And then, of course, here we have that when the beam is inclined, the perpendicular force will be a transverse force. Make sense? So regarding the moments that we have, as we mentioned here, bending moment and the torsional moment. So even in this case, we can use the axis of the beam to understand if the moment is a bending moment or a torsional moment. So in this case, we have to use the right-hand rule, and we can see where our thumb is pointing. So if we have a bending moment, it means that we are applying this kind of load. So by using the right-hand rule, we are bending the beam in this way. So the load, the moment will be in the perpendicular direction with respect to the axis of the beam, because we are bending in this way. So this is a bending moment. On the other hand, torsional moment is something that will twist our beam. So this is what we have. And in this case, still using the right-hand rule, our thumb points, it is aligned with the axis of the beam. Make sense? So again, bending moment and torsional moment. So now that we know what type of loads we have and how to identify each of them, we should be able to recall what type of stress each of these loads will produce inside our beam. So if we have a certain axial force, what kind of stress do we have? Normal stress. If we have a transverse force, what kind of stress do we have? Shear. If we have a bending moment, what kind of stress do we have? If we have a bending moment, what kind of stress do we have? If we have pure bending moment, we actually have a normal stress, because we are going to use the flexure formula, which we will see next. We obtain a normal stress. So we are going to recall the flexure formula as well. If we have a torsional moment, what kind of stress do we obtain? Shear stress. Yes.
That's just because of if you're looking at as layers, and then bending, it's not necessarily shearing the layers this way, shearing this way, right?
Yes. So basically, what happens when we have a bending moment? So when we have the type of deformation that we obtain is something that looks like this. Right. So basically what happened is that we have a change, so from the original configuration, that would be this one. If you look at how all the cross sections are oriented before and after the deformation, you can see that there is like a change in the angle along the axis of the beam. It means that basically every we call fiber in our material is either stretched or compressed. So if we have this type of deformation here, all the fibers that are on top are stretched because basically this portion becomes longer to go over that curvature. All these fibers that are on the bottom become shorter. So since we have this change in length, it means that we have a normal strain, which means that we have a normal stress. If we have pure bending moment. Make sense? Any other question about this? On the other hand, when we model a beam that is subjected to a certain torsional load, we imagine to have that our beam is made out of a lot of discs, kind of one, against each other. And then when we have that twisting load, basically each disc will rotate slightly with respect to the next one. And all these relative rotations are basically shear strains, which means that we have shear stress. Make sense? This is very important because basically this is the foundation of what we will see when we will look at combined loads. So right now, through this table, we're analyzing all the stresses one by one, which is something that we can do. But in reality, this is not something that happens. Because in reality, typically have more than one, sometimes even all of them together. Make sense? So we have a few more minutes. It means that we can start to see at what kind of equation we have to use in order to find the stress due to that specific load. So if we have a certain axial load, we said that we have a normal stress. So how do we find this normal stress due to the axial load? You remember? P over A. Exactly. Let's look now at the next type of load that give a normal stress. So if we have a bending moment, we said that we obtain a certain normal stress. Do you remember the equation that we have to use in this case? MC over I. And next time we will go on the details of all of them. What about transverse load? So transverse load gives shear stress. How do we obtain the shear stress due to a certain transverse load? V over A, that is one way to obtain the shear stress due to the shear force, but actually is a very simplified version of this equation, and that can be used. It can still be used, but only under certain circumstances. So if we want to find the average shear stress, we can use V over A, but again, it's an average. It's not accurate enough in certain conditions. If we want to be more precise, you remember which equation do we have to use? MQ. Anyone? There is a Q somewhere. This is the equation that you have to use. It's V Q over I T. This is called shear formula because basically it tells us the shear stress due to a shear force or transverse force. And then we have the other load that is responsible of shear stress in our material. We have a torsion, it's like twisting our beam. Do you remember the equation that we have to use to determine the shear stress due to the torsional moment? There is a J somewhere. Somewhere we should have also the load. So I would put here in the numerator, because typically, not typically, the higher the load, the higher the stress. So this must go on top. This over J. So even with this equation, there are limitations actually. This is an equation that we can use only when we have a circular cross-section. So it will be okay for this beam, but it will not be okay for other beams that have different cross-section. Any question about this? So we have a few more minutes. I guess we have time to look at the meaning of all these symbols. So here we have the very first one. Again, this is the normal stress due to a certain axial force. P would be the intensity of the load on that cross-section, and A is the area of that cross-section. Then when we move here, this is the shear stress due to the transverse load. And here we have VQ over IT. So V is the intensity of the shear force at that specific cross-section. Then Q is the static moment of the portion of the cross-section that is above the location at which we want to determine the shear stress. Then we have I, which is the moment of inertia of the entire cross-section. And then we have T, which is the width of the cross-section where we want to determine the shear stress. Then we have the third equation here. So this is the normal stress due to bending moment. M is the intensity of the bending moment at that specific location. Then I is the same of the I that we have here. So it's the moment of inertia of the entire cross-section. And then we have C, which is the distance from the neutral axis of the cross-section. And then we have the last equation. So this is the equation that relates the shear stress due to the torsional moment, the twisting moment. And then we have T, which is the intensity of the torsional load. J is the polar moment of inertia of the cross-section. And then C is the distance from the axis of the cross-section, which for a circular cross-section would be like the center of the cross-section. So for each equation that we see here, we will have a certain distribution of the stress over the cross-section. So this is something that we will go over next time we meet. I hope this helped a little bit to open a few drawers in our brain, and we are going to meet again Friday, this Wednesday. All right. Any question before we close? All right. Thank you very much.